let me take a look here. Let me make sure that I can be heard. I can be heard. We are recording for the homework on optimization. We had covered optimization at the end of, or for most of last class. And so here we're heading up the homework. Number one is review, in some sense. What two non-negative real numbers add to 70 and have the largest possible product? All right, so here the way that we have framed these was in the operations research model is to have some type of thing that you're trying to maximize. Objective function is what you're trying to maximize or minimize, and here is there's some constraint. You know how we roll two non-negative numbers. We don't know what they are. We need to name them, x and y. We need the numbers that add up to 70. That's a constraint. They sum to 70, largest possible product. You want to maximize x times y. Here we're going to get that it's 35. Let's take a look here. Oh, but they're going to ask us, let x be one of the numbers. Oh, they told us, let x be one of the numbers and let p be the product of the two numbers. Write the objective function in terms of x. And so here's x. And so you want to write in terms of x, we would say y is equal to 70 minus x. And then we would go up here and plug that in for y. The objective function then, I think they're calling it p. The objective function p is then p equals x times y, which is x times 70 minus x. The interval of interest. Well, the question is, what does this mean? This means is what are the bounds on x and y? Well, you have to add up to 70, right? So they both, well, in this case, let's make it x, right? So we can just say on x, right? So then x needs to be positive. They told us that. And then in order for p to be positive, then we want x should not be more than 70 because of 70 minus x. All right, so if y is 70 minus x and we want y to stay positive, then we need 70 minus x to be positive. And so that means 70 is bigger than x, or x is less than 70. The third question then says, okay, let's get to some derivatives now. I've got the function p now depending upon only x is x times 70 minus x, and we just now distribute and we fly through this. 70x minus x squared, I want to maximize or minimize p. The derivative of p is what we need to find. P prime of x is 70 minus 2x, and lo and behold, 70 minus 2x equal to 0 means that 2x is equal to 70, in which case x is 35. Y is 70 minus x, and as we had alluded to before, x and y should be picked to be the same thing. 35. Let's make sure we answer the question. The numbers that have a sum of 70 that have the largest possible product are, use a comma to separate 35, 35. Number 2. As we were saying last time, 32 looks like the adjoint problem, where now it tells us to find the minimum possible sum, given that the area is 89. This one may look super funky. Let's take a look. They're calling it S. Again, we're going to label, are they going to call it X? What is the objective function in terms of one number X? So they want one thing to be X. We're going to call the other thing Y. And then they want us to go ahead and solve for Y in terms of X. So we know we're forced to have a product of 89. And now we want to minimize the sum. Okay, so first step again is solve for Y. Right, so Y is equal to 89 over X. And again, as we said before, the point of doing this is to then create S as a function which is currently a function of X and Y to be only in terms of X. And so then this goes here, and then we get S as a function of X is equal to, I'm sorry, let's do this. S is currently X plus Y, but now this is equal to X plus 89 over X, and that is what they want here. We want the smallest possible sum. X is allowed to be anything. We were told that it was positive, but then the other one can be whatever we want, right? So 0 to the whole thing. For any X, I can find a Y to multiply by it and get 89. X can be any positive number at all. Now, what are the two numbers? Let's see. So now I want to make this thing as small as possible. Then what do we have? I want to minimize this function now. S of X is equal to X plus 89 over X. We're talking about taking a derivative, of course. 1 plus, or in this case minus 89 over X squared. Of course, we want to set that equal to 0 and solve, because the maximum or the minimum occurs when the derivative is 0, when you're smooth enough. So X squared is equal to 89, and it looks like X is equal to plus or minus the square root of 89. Again, looking at the context of the problem, we wanted two positive real numbers, and therefore instead of taking the minus, we would take the plus. So by the context, it is the square root of 89. I need to recall that X times Y is 89, and X is now the square root of 89. And so Y is equal to 89 over the square root of 89, which actually turns out to be the square root of 89 if you rationalize. And again, X and Y should be the same. There's a square root button in MyMathLab. Use it. Square root of 89, square root of 89. Working on the video for the homework. Taking any questions at any time. Classic problem here. Got some questions here. Okay, excellent. We'll roll along. A rectangular pen is built with one side against the barn. If 1,400 meters of fencing are used for the other three sides of the pen, what dimensions maximize the area of the pen? A rancher plans to make 4 identical and adjacent rectangular pens against the barn, each with an area of 25. What are the dimensions of each pen that minimize the amount of fencing that must be used? Okay, so we'll answer 1 and 2, or A and B separately. Let's take a look here. Oh, I guess we should also look at what question's being asked. So the first one is, let A be the area of the rectangular pen, and let X be the length of the sides of the length of the sides perpendicular to the barn, write the objective function in a form that does not include the length of the side parallel to the barn. All right, so let's include that. So they're being nice in terms of that they're helping us to set up the question. All right, great. So then we're talking about, they've told us to label, let A be the area of the rectangular pen and let X be the length of the sides perpendicular to the barn. So this is X, this is X, this is X, this is X, and this is X. Write the objective function in a form that does not include the length of the side, that does not include the length of the side parallel to the barn. Okay, so if that's X, then we've got what? So we need the area of the whole thing, right? Okay, so then what is this? So if this is X, then this is 25 minus X. And this is 25 minus X, right? So I guess we should write it this way. It's 25 times over X, right? The area is 25. 25 over X, 25 over X, and then 25 over X. A rectangular pen is built with one side against the barn. 1,400 meters of fencing is used. So what is it that we know? So the area of this thing is then what is it that we have? We have, I guess we can call this Y. Let's call this Y. So if we call this Y, then we know that 1, 2, 3, 4, 5, 5x plus Y equals 1,400. And we know that we want to maximize the area of the whole pen. We're using that for B. So we're going to maximize the area of the whole pen. Then we want to know, so we've got this without the 25. So here's the area. We want to maximize that. And then we've got this thing like this. That's X, that's X, that's X, that's X, and this is X. And then this is Y. And we got 5x plus Y is 14, and we want to maximize the area. The area is X times Y. And so we know the deal. Y is equal to 1,400 minus 5x. And the area is equal to X times 1,400 minus 5x. A is now a function of X. And I think my MATLAB is rolling that you can just go ahead and leave it like that. Did they ask us actually to solve this thing? Let's take a look. The interval of interest, well, we have this now, is X times 1,400 minus 5X. Interval of interest, we need X to be positive, and we need 1,400 minus 5X to be positive. So we just solve for x there. 1400 is bigger than 5x. Divide both sides by 5. 1400 divided by 5. 1400 divided by 5. 280. 280 is less than x. X is less than 280, bigger than 0. Interval notation, 0 to 280. All right, to maximize the area of the pen, we're talking about taking a derivative after we distribute 1400x minus 5x squared. That's a of x. The derivative, 1400 minus 10x. Need that to be 0. 140. 1400 equals 10x. Divide both sides by 10. X is 140. And then you solve for y. I think they asked for both dimensions, right? So long and the side parallel to the barn side, so the length of the sides perpendicular should be 140, and then you can find the other ones by solving for y. X is 140, and then y is 1400 minus 5 times x. 1400 minus 5 times 140. 1400 minus 700. 700. For B, they're asking us a different question. I was mashing A and B together. A rancher plans to make 4 identical and adjacent rectangular pens against a barn, and now we'll give you the area of each one. What are the dimensions that minimize the amount of fencing used, right? So now we have x, 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 right? And then we've got y. We can do all sorts of things, but if we do y, 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 I wonder if we label that way, whether that's going to give us what we want. Oh, I think we can do it either way, right? I'm debating. We could make this whole thing y and then do y over 4, or we can call them each y and then multiply by 4 at the end. I think we're going to do it this way, right? So then we know that x times y is 25, and now we're trying to minimize, that's 5 minimize 5x plus 4y. We know the deal. We're going to make y as a function of x. Plug that in. 5x plus 4 times 25 over x. You can see here that, how this problem gets framed is dependent upon how you label, and that is not a coincidence. I can call this the perimeter. Let's see what letter they use. L. Let x be the length of the sides perpendicular to the barn, and let L be the total length of the fence. Write the objective function, L, right? So now we've written it as um, 5x plus 100x. 100 over x. X is allowed to be whatever you want as long as it's positive. And the minimize, now we've got to find derivatives. They're calling it L. L prime of x is equal to 5 minus 100 over x squared. That equals 0. That means that 5 is equal to 100 over x squared. 5x squared is equal to 100. X squared equals 20. X is equal to plus or minus the square root of 20. Again, because x represents the side of something, we're taking the plus, the square root of 20. You got to be careful about how MyMathLab rolls. 20 is 5 times 4, and so square root of 4 is 2. 2 square root of 5. They may prefer that as x. And then we know that y is 25 over x. So y is equal to 25 over 2, the square root of 5. We'll go ahead and we'll rationalize that. This is equal to 25 over 2 square root of 5, and then we'll multiply by root 5 over root 5. This is 25 root 5 all over 2 times 5. That is 5 root 5 over 2. For y. All right, and there's x, and there's y. Okay, so the idea remains the same, that setting up the problem is usually the hardest part, and then really about labeling, trying to find out what it is that you're trying to maximize and minimize, what is the constraint that you've been given. Number 4. A rectangle is constructed with its base on the x-axis and 2 vertices on the parabola 49 minus x squared. F of x equals 49 minus x squared. I will bring this back home. Oh, actually, we need to zoom out. It's this thing. Zoom out a little bit more. Perfect. It's this thing. So what are we trying to say? We're trying to say that we're going to take this thing bring it over here, and the question is, we're going to create some rectangles. Right, we're going to do something like this. There's one. Let's get this orange out here. There's another one. Right? So out of all of these rectangles, there are infinitely many. Which one is going to give us the largest area? Right, so we got a label. So again, it's the area of a rectangle, so it's the length times the width. So we're going to pick an x. We want this to be some x. And again, we want the y value, 49 minus x squared is the y value. So that's the constraint, and we're trying to maximize the area. So we're trying to maximize the area. So the area function we know is x times y, and we know that the y coordinate is 49 minus x squared. Okay. So when we do this derivative stuff, we'll find out where the x value should be in order for you to create your rectangle with 2 of the edges two of the vertices of the rectangle on the graph. I think this is what they want for part A, x times 49 minus x squared. X needs to be this particular x. Let's see if they told us where x should be. A rectangle is constructed with a base and two vertices. What are the dimensions of the rectangle? Here it looks like 49 minus x squared should be bigger than 0. And so we need x squared less than 49. And so the interval of interest for the objective function, this is technically -7 to 7. The x that I chose actually should be from, I was wanting x to be from 0 to 7, and then I was going to reflect. But I think they may want this one, because they made no indication that x should be positive. Its base is on the x-axis, and two of its vertices. Yeah. In the rectangle, the maximum area, the shorter dimension is this, and the longer dimension is this. All right, so then let's go ahead and find it now. So we'll distribute a as a function of x only is 49x minus x cubed. A of x is equal to nothing because I'm interested in the derivative. It's 49 minus 3x squared. We want that to be 0. Nice and funky. 49 is equal to 3x squared. X squared is equal to 49 over 3. X is equal to plus or minus the square root of 49 over 3. And so x is equal to plus or minus 7 over the square root of 3, which we can rationalize to be 7 square root of 3 over 3, plus or minus. Now, I actually do think it's either one, right? So this makes me believe that they actually want the plus. Let's see how it's phrased. So it looks like, and so we're going to use this to find what y is. So the shorter dimension is about, so they want the length of this thing. So then the length of this, so what we did was we found the coordinate. So we know that this coordinate is 7 square root of 3 over 3, but the actual length is 2 times that. So the actual length, or I should say the width, is 2 times 7 the square root of 3 over 3. 14 square root of 3 over 3. The height is just the y-coordinate. Y is 49 minus x squared, but x was 7 root 3 over 3. So this is 49 minus 7 root 3 over 3 squared, which is 49 minus 49 times 3 over 9, which is 49 minus 49 over 3, which is 3 times 49 over 3 minus 49 over 3, which is 2 times 49 over 3, 98 over 3. That's going back and getting the y-coordinate. So here's the x dimension, here's the width, and here's the length. Let's see how we're about to put this in. In the rectangle, the maximum area, the shorter dimension is, all right, we need to see which one's actually shorter. It may be obvious. 98 over 3 is longer, so the shorter one is the square root of 14 square root of 3 over 3. How are they wanting us to put this in? Round the 2 decimal places. So then you would round 14 square root of 3 over 3, round this to 2 decimal places, and then round 98 over 3 to 2 decimal places. And then multiply, and that gives you the area. So then it's 98 over 3 times 14 square root of 3 over 3. And then round to 2 decimal places. We've got a rectangular tank with a square base, open top, volume of 42,592 feet cubed is to be constructed of sheet steel. Find the dimensions of the tank that minimize the surface area. We talked about a box like this that we would have. We want to put something in it. The thing we need to put in it is pretty big, so it's got to hold this much volume. Right, so the volume in this thing, volume 42,592 feet cubed. And now we want to make this from steel. How much do we need to make the minimum surface area? So as you know, we got a label. We're going to label X, Y, and Z. And we know now this is in 3 dimensions. And in this world of calculus that we're in, all of the stuff needs to depend on one variable. So the hope is that we can go ahead and make everything in terms of X. We can start off by realizing that they said that the base was a square. And so they're trying to simplify things because we only know one variable. So that means that X and Y are the same. And so this is X. If we wanted to find, so let's be clear, they want us to minimize the surface area given that this box has to hold 42,592 feet cubed. Okay. So let's go ahead and find a formula for the surface area. So the surface area is defined to be the area of all the sides, right? So this top is open, so we're talking about the sides and the bottom. The area of the bottom, the surface area, is equal to the area of the bottom, which is X squared. This is the bottom. And then the sides are going to be X by Z, and there are 4 sides, plus XZ, plus XZ, plus XZ, plus XZ, remembering that there was no top. The surface area as a function of X and Z is equal to X squared plus 4XZ. And we'll remember that this, so again, here we are, the surface area is a function of 2 variables, but we need it as a function of 1. We'll use the constraint to say that Z times X times Y needs to be 42,592, but again, we said that X and Y are the same, so that ZX squared is 42,592, and so Z is equal to 42,592 divided by X squared. We know the deal. We'll plug that in here, and then S will be a function of X only. S of X is equal to X squared plus 4X times 42,592 over X squared, and we've got to do some multiplication. X squared plus, these X's cancel, but 4 times 42,592. 170, 368. 170, 368 all over x. We know we want to take a derivative of this, set it equal to 0, and solve. The derivative of this is 2x plus, in this case, it's minus 170, 368 all over x squared, and we would like for that to be 0. One of these tricks, we'll multiply everything by x squared. Gives us 2x. Actually, let's do this. Let's put these things on both sides, and then we'll cross multiply. Either way works, but I want to be consistent. I've been doing it this way before. Over x squared equals that. Then we'll cross multiply. 2x cubed equals 170, 368. And the hope is that they actually gave us a perfect cube, right? So 170, 368 divided by 2. X cubed is 170, 368 divided by 2. And let's see what that is. X cubed equals, divided by 2. 85, 184. Cube root. Is there a cube root power? We'll raise this to the 1/3 power. Let's see if it's going to be nice to us. Equals 44. How nice is that? X cubed equals, let's go back. $85, 184. And x is 44. Units, feet. So the objective function is this function here, x squared plus 170, 368 over x. We can let x roll anywhere from 0 to infinity. And then the height we don't know, but the side length we just found out was 44, and we can get the height by doing this. Z equals 42, 592 over 44 squared. So to get Z, that equals 42, 592 over 44 squared. We can only hope that that number is nice. Yeah. Excellent. So again, this is notoriously the longest part of Calc 1 doing these optimization problems. But now you can see that equipped with this stuff, we can actually solve some interesting problems that interest business and economics in all sorts of areas. Similar question, including the cost here. A storage shed is built in the shape of a box with a square base. It is to have a volume of 729 cubic feet. The concrete for the base costs 7 feet per square foot. The material for the roof costs $8 per square foot, and the material for the sides costs $7.50 per square foot. Find the dimensions that minimize the cost of the shed. Okay, so we're assuming that the shed is just going to be a straight up box, no normal roof, right? So it's just the top of the box, it feels like. Square base again, so we got X, X, Z. Minimizing the cost. So we've got, what's the volume? 729. So I know that x squared z needs to be 729. right? While we're at here, let's just get it, 729 over x squared. And now, what is the cost function we're trying to minimize? Well, units are per square feet, and so we'll need the cost of all this stuff on each one of the sides. The concrete base costs $7 per square foot. How many square feet are at the base? It's x squared. X squared feet squared. And so the cost of the base is 7x squared. Material for the roof is also x squared. So the roof, the area is x squared. The cost is 8x squared. The sides are zx, and there are 4 of those. Zx, the cost is on the sides $7.50. 4 sides, $30 for all of that. And we are good. So then we've got 15x squared plus 30 times zx. And of course we know that z is 729 over x squared. Times x. And then we get to the work of what we just did before. 30 times 729 over x. And then we do what we just did in the previous problem, right, and practice that out. So then we'll take the derivative, set it equal to 0, and solve and figure that out. I will leave that to you to figure out. They're calling it C. So then that is the cost function as a function of x. We'll fill in this other stuff. 30 times 729 in this case. $21,870 over x. We'll put that here, and then again, it's at the interval from 0 to infinity. And then take derivative, solve like you did last time. It looks like they have us in mind to put a nice answer there, so you should get a nice answer. If it doesn't ask you to round or keep it exactly as it is, then it seems like it's going to turn out nicely. All right, let's see if there's anything else. I think that is it. Perfect.